and good morning. So let me share my screen and let me start the story of electrical impedance tomography. One of the main applications of this imaging method is heart and lungs imaging, and it looks kind of like this. This is actually, this picture of this guy is from my PhD thesis from 1999. I had to quickly draw something to show the idea how this measurement is done, and apparently this picture will live forever. It's been used a lot. So here it is. There's kind of a belt of electrodes around the chest of this person, and we feed electric currents through these electrodes, maybe so that there's electricity going in one of the electrodes and coming out of another one, or there can be more complicated ones. This is repeated for many current feeds, and always it's measured what is the voltage at the electrodes resulting from the current. So that's the measurement data, the voltage matrix coming from different current feeds. And then the goal of electrical impedance tomography is to calculate a picture of electrical conductivity inside the person. So the picture could look something like this, although this is round and the patient is not, but approximately. So this would be the heart, the red one filled with blood, and the lungs filled with air would appear as blue. Electricity has a harder time going through the air-filled lungs and easier time going through the blood-filled heart. Let me show you a picture. I want to show a video here. This is from Jennifer Muller's group. And we can see how, where did it go? Come on. So here on the bottom, you can see the heartbeat rhythm, and on the top here, you can see both the heart beating and the lungs filling with air and emptying. In Jennifer's group, she has shown that this is the only way you can measure how much air is actually going to the lungs of a little child, which is important to measure in the case of cystic fibrosis, for example. So in medical imaging EIT, the promise of EIT is that in some cases it's the only way to see something that the doctor wants to see. Also, as you can see, the image is kind of blurry. It's inherent in this very ill-posed and nonlinear inverse problem. Well, in medical imaging, there are also other things you can try. For example, measuring vocal folds. This is from our previous research project. This is another one for the same. This one is still, the jury is still out. Is it a good method for vocal folds? But now a very active research topic in FAME is to try to see if we can image stroke in the brain using electrical impedance tomography. So this is together with University of Eastern Finland, University of Tampere, Aalto University, and also Helsinki University Hospital. So this is a big collaboration. So we hope on one hand to use something like you see in these figures, some kind of a helmet like that, to see in the ambulance already if the stroke is caused by a blood clot preventing blood flow, or is it a ruptured blood vessel, so then there is a bleeding in the brain. It's important to know which one it is, because the symptoms are the same, but treatments are very different. Another interesting application is monitoring a stroke patient who is in intensive care unit, because currently, to check if everything is okay and there is no new bleeding, the patient has to be taken away from here and brought to the CT X-ray tomography device elsewhere in the hospital and then bringing back. With EIT, we hope we could monitor in real time, just keep monitoring for 4 days and then the doctors would see what is going on. Electrical impedance tomography is a very classical topic in Finland. For example, Erkki Somersalo, the supervisor of many PhD theses in our community, he was already a pioneer in this topic in the 1980s and 90s. Also, I want to point out that, for example, the work in Kuopio, Aku Seppänen, now Aku Ursin, also Marko Vauhkonen, Ville Kolehmainen, and others, there have been super interesting uses of EIT. I mentioned a couple. So this is seeing cracks in concrete. So there were some cracks caused in the concrete deliberately here, and you can see where the cracks are using electrical measurements at the boundary of concrete. So you could, for example, check that Prisma supermarkets are not collapsing. You can check the pillars that they are fine. Another one which I really like, also by Aku and collaborators, is seeing how water is seeping inside concrete. I love this work especially because the control picture here to be compared with EIT was done with a neutron beam. So this was done in a nuclear research center, and water, the hydrogen is scattering neutrons very effectively, so we can see a comparison image. I love this kind of science. It's wonderful, both electricity and nuclear. Okay, hopefully I made the case that this is a fundamental inverse problem with many applications and also deep roots and history in the Finnish inverse problems community. So now for the very new development from my team and Matti Lassas and others, we actually found a new way to look at the electrical impedance tomography reconstruction problem, which is known to be very ill-posed and also non-linear. So this is a very complicated slide. Let me just, there's no way to explain everything in detail, but let me give you a kind of an overview what is happening here. So if this is our original conductivity, and the blue arrow gives that this is our voltage matrix measurement, so then it's possible to use basically the method by Nuutti Hyvönen and Henrik Garde, a little bit adapted to this situation, to find the so-called Dirichlet-Neumann map, which is a mathematical ideal measurement model. We can solve a boundary integral equation. It's a nonlinear process, and we get a complex function we call t tilde odd that looks very colorful. These colors up here and these down here are numerical errors coming from the noise in the data. So we cut them away with a Gaussian bell curve. So we get something, so to say, the stable information from the measurements is here. We take the Fourier transform of the columns of this one. We make a phase correction. We get not complex valued anymore, but real valued. Some integral step, some nonlinear step. And now I think the curious thing happens. All of the ill-posedness of EIT is in this linear step of one-dimensional deconvolution and a little bit of ill-posedness in recovering from the sinogram. So this is curious. The EIT, which is the fundamental nonlinear inverse problem, it contains one-dimensional linear deconvolution and also the classical X-ray tomography problem. It's hidden inside EIT, and we can decompose EIT like this. Now, of course, this will lead to new imaging possibilities. Here are some machine learning things done by Siiri Rautio, my former student. So she sharpened the sinograms using machine learning, and then we can get these completely new kinds of things, measuring such phantoms in the laboratory. We get a blurred virtual sinogram without any X-rays, but as if there were X-rays. We sharpen it, and then we can reconstruct the thing we see in the tank. And what is new about this? These yellow curves that are kind of like X-ray images of the orange target, but no X-rays are used here. It's all based on electricity, no ionizing radiation, and these yellow profile functions that are exactly like they are in X-ray tomography, them we can compute from electrical measurements, and this is something completely new. Now, time will tell what are the best uses of this information, but I must say I'm quite excited about the new avenue of investigation this opens. I would even think that this is what we call it VHPT, which is for virtual hybrid parallel beam tomography. Hybrid meaning that we combine two different measurement energies, so to speak, electricity and X-rays, but virtual hybrid because the X-rays are not actual ionizing radiation, but everything is done with electricity. So exciting times. I'm really curious to see where this goes next. Actually, we already tried this method on human data, and it seems that for human data, this method is extremely robust against unknown boundary of the patient and also the locations of electrodes. So it's quite interesting to see what we can do with this new methodology. If you're interested, our paper is in archive and it will soon appear in Applied Mathematics for Modern Challenges. Oh, I had one more slide, so I wanted to show how these gaps, we just cut this phantom in half and we saw how this gap becomes visible with different methods. These two are our VHPT. This is the so-called D-bar method. Okay, that is 15 minutes of fame for this morning.